So we've actually kind of looked at polar coordinates. We just didn't call them polar coordinates. So some of it will look familiar to you. Other parts of it will be new. So first, let's talk about what polar coordinates are. So we have been working with numbers in a coordinate plane that are identified by the rectangular point xy. These rectangular points describe the horizontal and vertical placement of that point on my rectangular grid. Okay, so that's just information. That's something that we've already been dealing with. We maybe just didn't look at it in this aspect. So every point that we have plotted thus far has been a rectangular point because it is point xy that is describing the horizontal and vertical location from the origin. But what if we didn't want to describe the horizontal and vertical location from the origin? What if I wanted a circular location? So a polar coordinate is just this rectangular coordinate converted into the angle at which this point exists and the distance from the origin to that point. So every xy coordinate can also be identified using a polar point r theta, which describes the angle of the point and the distance r. R can be either positive or negative, but this, or its positivity kind of depends on the angle that we're looking at, and you'll see why in a minute. Before we get too far into the conversion process, I just want to look at what a graph of polar coordinates looks like, because you might have to freehand some on your homework, which I know you're super excited about. So if I were looking at a polar graph, as you probably already guessed, it is composed of a circle, and on the circle, we have units heading off from the origin along the diagonals and along the axes. Each of these units corresponds to a unit of length. So this would be a distance of 1 away from the origin. This line would be a distance of 2, a distance of 3, and so on. So we count our distance by these rings that go through my circle. On my circle, I also have angles. These are the same angles that we already identified on our unit circle. Because this isn't that large, I'm not going to write them all in. But the major ones, of course, are our 0 angle, which is always to the right. Then we have our 30, our 45, and our 60. And we also know that all of these have a corresponding radian measure as well, but for ease, I'm just going to put the degrees. We know straight up and down is 90 degrees. And then it just continues on the same as our unit circle does, outlining the same major angles. It's very hard to draw. I don't either.
It's a spider web.
It is actually, it very much looks like a spider web. And then when we get back to 360, we don't call it 360, we call it 0. So all of the angles on here exist between 0 and 360 degrees, but not including not including 360. If we were thinking about these in radians, it's the same as saying that right angles all exist between 0 and 2 pi. The center of my polar coordinate system is called the pole. And my 0-degree angle is also called my polar axis. I'll see you later. Everyone okay so far? I will give you a second to finish drawing the graph because I'm sure this is where most of you are getting hung up right now. And then we will start looking about how the coordinates for my polar point correspond to the actual point on the graph. Okay, so when I look at a point on my polar coordinate system, this is a point that is created by an angle starting at 0. And each of these points has a distance from my polar center, so my center pole. Which means that my coordinate is r comma theta. This is the same r and theta that we've actually already calculated in the polar form of trigonometric form of complex numbers. These are the same values, we're just looking at them now in their own coordinate system. So this r right here is the distance from the center of my pole out to point P. When it goes forward along the angle, that means my r value is positive. So it could be +4 or +2 or +3 square root of 2. Whatever the r value here, it is positive. I did mention that it's possible to go ahead and have a negative r value as well. So this means that I had an angle theta that created my point, but instead of walking forward along that angle, I walked backwards. So this would still be r, but this would be r in the negative direction. A positive r indicates a forward movement along the angle. A negative r indicates a backward movement along the angle.
So even if it's going down.
It's walking backwards. There's a difference because I could have an angle here and I'm walking backwards, but it takes me up. We'll do some examples that'll make more sense. So a forward movement indicates a positive r. A backward movement indicates a negative r. Okay, it is possible to have a negative distance on a polar axis or on a polar coordinate system. I know that sounds really confusing, so of course we are going to go ahead and do a couple examples and hopefully it will make more sense. So the first one that I would like to do is I would like to graph the point to, say, 150 degrees. I'm going to draw one coordinate system and then we're going to graph multiple points on it. Okay, so this is just the first one that's going on here. I know. I'm going to do this one in blue. And then we'll do different colors for the other points. So when I go to graph this, what do you think the first thing I need to identify from this point is? The angle. I have to know which angle my point is going along before I can find the distance or identify the distance. So I need to find 150 degrees on the circle. I know this is 0 degrees, so where's 150? Which quadrant? 2. It's going to be approximately right there. So that's 150 degrees. need to do is I need to find a distance of 2 from the center of my circle. So I'm just gonna draw a bunch of these. That way we can start counting our distance. You don't have to be perfect.
Mine's square. Square. To be right around.
They don't have to be perfect,
No,
it's fine.
listen, it's square at the bottom, but like rounded square, and at the top it's curved, so it's like, it looks like a face.
Okay, so we identified the angle, that's awesome. So now I'm going to pretend that I'm a person standing right here at the pole. I'm gonna turn and I'm gonna face that 150-degree angle. Along this angle, am I walking forwards or am I walking backwards to get to a distance of 2? Forward, how did you know that? Because R is positive. So from this pole, 0, 0, I'm gonna walk 2 units along that angle of 150 degrees. We're gonna call that point A. So I have now put point A on my polar coordinate. Great. Does that make sense?
Yeah.
We're gonna do another one, of course. This time, I would like to do the point, I don't know. Oh, wrong one. -3, 300 degrees, and this will be point B. When I'm graphing this, what is the first thing I need to find on my circle?
Angle.
The angle theta, so that's 300 degrees here. Which quadrant is 300 degrees in?
Fourth.
Fourth. It is right here. Approximately. Once I identify the angle, I pretend I'm a little person standing at that pole. I'm gonna turn and I'm gonna face my angle 300. Am I walking along that angle or backwards away from the angle? Backwards, why? Because it's a negative R. I do suggest that if we're walking backwards, we go ahead and extend our angle with a dotted line, just so I make sure I'm still in line with that 300-degree angle, because it did dictate my point, okay? So facing that 300, I'm gonna walk back 3 units, so 3 rings. And I'm gonna put my point. So even though these 2 points looked completely different, they ended up extremely close to each other and in the same quadrant. Okay, so that negative or positive direction really does affect where my point lies. Any questions on that? Anybody super duper confused? Random question. I just put the point -3, 300 on my graph, right? Is there another polar coordinate that would have landed my point in the same place? Or was -3, 300 the only way to get to this point?
3, 120.
How'd you come up with 3, 120, Gabe?
30 degrees away from 90. And what it looks like it.
Mm-hmm.
And 300 is 30 degrees from 270. It's the opposite side of the y-axis.
Perfect. So I found the angle opposite this one by subtracting 180, which gave me 120. And then if I'm facing 120-degree angle, I walk forward 2 units. These 2 then are equivalent because they give me points in the same location. There's more than one point or more than one coordinate pair that will give me the same point on a polar axis or on a polar coordinate system. Yes.
Where are you starting? This, the lines, you walking you backwards.
We start at the center. So if I walk backwards, 1, 2, 3.
But how did you just go the other way?
Because it was a -3, which meant that I couldn't walk forward.
So how do you find the other one? Like if you don't know the negative, how do you know if it's negative?
Well, you have to, like, you would have had to, like, if I just had 300, or,
If you had like a point,
uh-huh.
how would you determine like if it was a -3?
Oh, okay. Well, I would face whatever angle it gave me. And if I know that my point has to be in quadrant 2, but I'm facing 300 degrees, would I walk forward into quadrant 2, or would I have to walk backwards?
Let's know.
I'd have to walk backwards. So that's how I know it's a negative. But that will come when we start actually doing the conversions. That's a really good question though. That actually brought up a really good point. Actually, I'm gonna save that point. I'm gonna save it because it's gonna fit better somewhere else. But that was a really good question. So if we don't know, like if I know my distance is 5, I just need to figure out if it's positive or negative. We always start by facing whatever angle I have, and then determining, okay, if I walk forward, is it gonna put me where I need to be? Right? So if I walk forward 3 along 300, but I know my point has to exist here, I know that couldn't have worked. I have to know where I need to end up in order to know whether my distance has to be positive or negative.
How did we know to put that be there then? Why didn't we?
Well, we plotted it first. I'm gonna show you how we check when we start converting. I told you where that point had to be. That's how we knew. Okay, so actually, he's kind of jumped ahead a little bit. So let's go ahead and head there as well. We're not really skipping anything. So we're gonna now start looking, oh my gosh, at the conversions between polar and rectangular coordinates and their coordinate systems.
I think a lot of space.
The examples will, but the actual conversions, no. So the first set of conversions are identifying the relationship between my x and y and my r and cosine, and sorry, r and theta. Does anybody know anything that relates the two of those? We wrote it down.
What is sine and cosine?
What relates x and y to r and theta? I'm hearing sine and cosine, and that's definitely right. In fact, x is equal to r cosine theta. Didn't we write that down last lesson? We also wrote down that y is equal to r sine of theta. This came directly from that trigonometric form of complex numbers. Yes,
Does R still mean magnitude?
just again.
Does R still mean like the magnitude? Like you can still
Yeah, still distance. It's still a distance, just now it could be positive or negative. The other set of conversions that we're going to need are how to relate the r's and the thetas back to the x's and the y's. So the first one is that I know r squared is equal to x squared plus y squared. And from that, I get that r is equal to the square root of x squared plus y squared, which is that distance, which is that magnitude that we've already done. Additionally, I know that tangent of theta is equal to y over x, which means tangent inverse of y over x will give me my thetas. Okay, so these we've already done, except we use a and b, but it's still the same process. I would like to use exact values, so you will need your unit circle out in case you don't already have it out.
I don't think I could sign the argument.
Yeah.
You just gotta ask medication on.
Hold on. That's our there, dude.
So then we're going to go ahead and jump into our first conversion example. I know you're all so excited. There we go. I know, but I tend to zoom out a lot and then I run out of room. So this example says, if r theta equals 4, 7 pi over 6, are the polar coordinates for my point find the rectangular coordinates. So this is the example that we're starting with. Again, if r theta is equal to 4, 7 pi over 6 are the polar coordinates of my point P, find the rectangular coordinates of that same point P. If I'm changing into rectangular coordinates, I'm trying to find the x's and the y's. Some people do find it helpful to write out the conversion that we're doing. So we're going from r theta into xy. That is the conversion that I'm trying to make right here. So if I'm trying to find x and I'm trying to find y, which of those conversions above do you think I'm going to use? R cosine theta and R sine theta, because those are the only x and y's that I have. So my x is going to be equal to r cosine of theta, and I'm just going to go ahead and fill in the r and the theta that came directly from my polar point. And then I'm going to fill in the r sine theta, again putting in the r and the theta from my polar point, and I'm just going to simplify them out. I do want exact values, which means my x coordinate here is going to be equal to 4 times cosine of 7 pi over 6. So I need to go to my unit circle and figure out what cosine of 7 pi over 6 is equal to, and then multiply that by the 4. What is cosine of 7 pi over 6 equal to? Well, it's 210 degrees, but negative square root of 3 over 2. You're okay. Anybody else get negative square root of 3 over 2? Okay, so when I simplify that out, I actually end up with negative 4 times the square root of 3 over 2. Can I simplify that at all? Yes, how? Perfect. 2 comes out of 4 and it comes out of 2, so when I take it out, I get negative 2 times the square root of 3. So that is the x coordinate for my rectangular point. Anybody confused by how I got that? Find the y. Anybody else get negative 2 as my y coordinate? Show of hands, come on. Be confident in your answers. You got what, honey? How'd you get positive 2? What's sine of 7 pi over 6? Oh, you just forgot to write it? Oh, okay. So we should have gotten sine of 7 pi over 6 was negative 1/2. Negative 1/2 times 4 is negative 2, which means the polar point for 7 pi over 6 is equivalent to negative 2 square root of 3, negative 2. Of course, I don't just blindly accept this. I should rationalize it and ensure that these 2 points are in fact equivalent. In order to do that, I need to figure out the quadrant in which each of these points exist. If they match, then I've done my work correctly. So let's go ahead and take a look at the polar point first. What angle is 7 pi over 6 in? 2 or 3? 3. Should be just below that 180-degree angle. If I walk forward along that angle, am I staying in quadrant 3 or backing up into quadrant 1?
You're staying in quadrant 3.
Staying in quadrant 3, awesome. So this is an angle in quadrant 3, or a point in quadrant 3. What about this one? How do you know it's in quadrant 3, Nadia? Because they're both negative, which means from the origin 0, 0, I moved left, and then I moved down, also putting this one in quadrant 3. The quadrants match, so I did my work correctly. How do we feel about that? You should always check them to ensure that we did it correctly, because sometimes we could get more than one angle, and we have to be sure that we pick the correct one. Okay? Anybody super duper confused so far? Show of hands, how do we feel so far? So 1 to 5. Okay, actually not as bad as I expected, so I'm feeling pretty good. Nadia,
When you said that we might have more than one angle.
we're gonna do that one in a second. Yeah. Okay, so we did the conversion from polar to rectangular. Now let's go that opposite direction. So let's take a rectangular point and find its equivalent polar point. So this one says if xy is equal to the point -1 square root of 3, and these are the rectangular coordinates of point P, find then the polar coordinates of that same point P. The first thing I want to do when I'm presented with a problem like this is I need to figure out what quadrant my original point laid or lied in or was in. That's the correct one there. Lies. Okay, I need to figure out which quadrant my rectangular point -1 square root of 3 lies in on my rectangular coordinate system to figure out what the correct angle will be when I do the conversion. So what quadrant is that point in? 2, because from my origin, I went left and then I went up. So this is a quadrant 2 point. That is extremely important here. I like to write it out, so I know that I'm going from xy and converting into r theta, which means when I do the conversions, I need to find something that r equals, and I need to find something that theta equals in order to plug values in to find those numbers. So I like to start with r. R is the easiest one in my opinion. So how do I find what my r value is?
Square root of x squared plus y squared.
Square root of x squared plus y squared. Or the distance formula, whatever you want to think about it as so you remember it. I know -1 squared is 1. What is the square root of 3 squared?
3.
3. Which means I have the square root of 4, and what is the square root of 4 equal to?
2.
And -2. Remember, now I can have positives or negative r values, so I need to keep both of them as options until I identify the angle. Majority of time, I will say choose r such that r is positive, in which case you would just say 2. I didn't specify that here, so we have to accommodate for both.
Wait.
Yes.
Okay, finishing first and on.
Okay, so let's go ahead and find our angle. How do I find my angle theta?
The inverse of tan y over x.
Tangent inverse of y over x. I know my y value is square root of 3. Over -1 reduces to negative square root of 3. So I need to go to the back of my unit circle. I need to go to that tangent column, and I need to follow it down until I find where tangent is equal to negative square root of 3. There will be two angles. I want both of them. And we can go ahead and do it in degrees, just to make it easier. If you want to do radians, that's fine, Nicole. It is your choice unless I specify, but I usually don't, so I'm okay if you guys do degrees all the time, as long as you're doing all your work correctly. Molly, what'd you come up with?
I got 123.
Did you say 123 or 120 degrees? Okay, just checking. Right. So she got 120 degrees and 300 degrees. So that would be what, 2 pi over 3 and 5 pi over 3? Anybody else get something different? No. So those are the two angles at which my tangent value is equal to negative square root of 3. So here's the issue.
You don't specify.
I don't specify, which means I need to find the correct pairing between these angles and these distances so that my point ends up in quadrant 2. So I like to start with just picking one of the angles. Let's start with 120 degrees because it's a smaller and I like to work like that. What quadrant is the angle 120 degrees in?
Quadrant 2.
Quadrant 2, which means if I need to stay in quadrant 2, do I need to put the positive distance of 2 with that 120 degrees, or do I need to put the negative distance of 2? The positive, because I want to stay in that quadrant 2. What if I chose the angle 300 though? What quadrant is 300 degrees in? 4. So if I need to end up in quadrant 2, can I walk forward and stay in quadrant 4, or do I need to walk backwards? We need to walk backwards, so that means I would assign the negative 2 to the 300. Yes, ma'am?
If we were to put like either answer, would they both?
Unless I say you have to do R positive, then I would accept either answer. There will be times where I ask for 2 different rectangular or polar points that exist for this point, in which case I expect both of them. It is also possible for me to ask for 3 or 4 or 5 different polar points that are equivalent to that rectangular point. We found 2 of them. How possibly could I find another? Add or subtract 360, because all I would need to do is find other angles that are coterminal to these 2. So for example, if I wanted a third point, I would pick the positive because I like the positives more, and I would add 360 degrees to 120, which would give me a coterminal angle of 480 degrees. So it is possible to find up to 10 or 20 different angles that also exist here.
You just said the thing that has to be listed there.
I didn't write that here. If that's written there, then yes. But I didn't specify that. This is all theoretical. I could potentially ask you if I don't say it has to exist on the unit circle. If I do say that, then yes, this one would not work. At most, I usually ask for 3 different polar points that are equivalent to a rectangular. At most, I ask for 3, and this would suffice. Yes.
We could ask for 3, like where it's based off the unit circle, where it has to be less than 360.
There is no possible way of getting that, so no. No. If I say on the unit circle, at most you can give me is 2.
Okay.
Yeah, that's a good question. Okay, do we understand these 2? Because these 2, in my opinion, are the most important.
Is it 360 technically on the unit circle?
Technically, yes, but it's equivalent to 0, which is why we don't include 360. So if you said 360, technically that would just be the 0 angle. But yes. Are we okay on these 2? These are the most important part of this problem. If we don't get this, that's minor. But these 2 are the important ones. Anybody not understand those? Or understand how we got them? Are we still feeling pretty okay with this? This, fortunately, is stuff that we've kind of already done or I've already introduced to you. Now we're just doing a little bit more with it. What time is it? we're gonna pause here because we're about to move into equations and we can finish that up tomorrow. Okay, so your homework is on Canvas. You can definitely go ahead and get started on it, and it's due on Wednesday.